Hi, and welcome to 11.7, Part 2, Parallel Circuits. So now we're talking about parallel circuits. Diagram below shows three resistors connected in parallel to a 12-volt source, and it's saying what is the equivalent resistance. So you look in your reference table for the equivalent resistance formula, and here it is on page 4. Probably the weirdest equation on this page. So don't forget, it's the 1 over Req. That's what this equation is set up for. So you got to solve just for Req. You want to get it by itself just like this. We don't want to wind up with 1 over Req equals some random number. You take the inverse at the end to get the equivalent resistance. So let's write down the equation carefully. We'll substitute in for R1, R2, and R3. And now we're just going to solve for Req, and you could do that either by plugging these fractions in your calculator and it'll tell you a decimal. So if we do that, it would look like this. And then you have to still solve for Req, so we don't want that as our answer. It's not 1.25 ohms. You actually have to take the inverse of both sides, so you could just flip both sides, Req over 1, and then this is 1.25 over 1, you flip that, and 1 over 1.25. So basically Req is equal to 1 over 1.25. And then you get an answer. It's equal to 0.8 ohms. So the equivalent resistance is 0.8 ohms. We could replace these three resistors with one resistor of 0.8 ohms, and it would have the same current in the circuit. You have the same current here as you do at this position in the circuit, okay? In each branch, it's going to be different, but the total current with the three resistors in parallel is equivalent to this current if you just have one very small resistor. And as you can see, the equivalent resistance in a parallel circuit is always less than the smallest resistance. And the reason is because there's three paths for the current to flow through. So it's like there's more lanes in a highway that the cars have. So it won't be as much of a traffic jam, meaning there'll be less resistance overall and more current than if these were connected in series. But let's back up a little bit. Is there a different way that we could solve for this equivalent resistance? Maybe you didn't like taking the inverse. Well, if you don't want to take the inverse, you could also cross multiply. So let's do that. This is what we had when we did 1/2 plus 1/2 plus 1/4. We plugged it in our calculator. It popped out 1.25. Well, if you're solving for Req, you could also like cross multiply. So 1 times 1 is 1. This is equal to 1.25 times Req. And then you end up solving divided by 1.25. That cancels out. See how on this side of the equation, it looks like we did before when you took the inverse? You just flipped it, this 1.25 over 1, you just flip it. It's the same process. You still get Req is equal to 0.8 ohm. So you could either take the inverse of both sides to solve for Req. Remember that the reason we're doing that is because 1 over Req. We have to solve for just Req. So you could take the inverse, you could cross multiply, or if you're comfortable with your fractions, you could actually, from this step, you don't have to plug it in your calculator and get to 1.25. There's a different way you could do it. So let's do it that way. Let's just look at this in terms of adding the fractions together. And as you'll probably remember from your math class, to add the fractions together, they need to have a common denominator. So you look, what's the common denominator here? I would say 4. You want to make everything equal to 4. So to make this first fraction 1/2, if you want a 4 on the bottom, you have to multiply this by 2. And whatever you do to the bottom, you do to the top to keep the fraction the same. And we have 1 over Req is equal to 2 over 4. We're just doing, and then you do the same thing here to get a common denominator, plus 1 over 4. So 1 over Req is equal to 2 plus 2 plus 1. That is going to be 5 over 4. Okay, but we're not done yet. And now the reason I like doing it this way with the fractions is because when you do the inverse, you kind of have a nice fraction here and you just flip that fraction. So again, we're doing the inverse. Req is equal to 4 over 5. And that could be your answer if you want. Leave it in fraction form. Can't take off points for that. But if you want 4 divided by 5, that's also going to be 0.8 ohms, or 8 tenths, right? 8 tenths, 8 over 10. reduces down to 4/5. So if you like fractions, or if you want to, maybe you didn't like fractions, and I encourage you to try to do these problems by doing, the fraction way, because it's a good way to practice, and hopefully you get the hang of it, and you'll see it's not too bad. That is, if the denominators are nice, like a 2 and a 4 and all that stuff. But anyway, I'd spent a lot of time on that because with parallel circuits, finding the equivalent resistance seems to be the trickiest part. But the rest of it is kind of tricky too, so let's move on. I'm going to clean this up a little bit. Now they're asking for the total current, and they tell you the resistance and the voltage. So I would do Ohm's law, I is equal to V over R. So that's 12 over 0.8, and when you do 12 divided by 0.8, you get 15, and it's the current, so it's amps, 15 amps. That's like over here, the current is equal to 15 amps. I actually drew the arrow wrong the other way. The conventional current comes out of positive and into negative, just so you know. Okay, so letter C says, what is the current through the first 2 ohm resistor? Okay, so that's going to be different from the total current. In the first 2 ohm resistor, they're looking for the current at this position. We could call that I1, and this is the total, IT. So now we have a resistance of 2 ohms, so R1 is equal to only 2 ohms. We're not going to use the equivalent resistance because we're just looking for the current through this branch. What else do we know about this branch? Well, it's a parallel circuit, so let's look at the relationship. In parallel circuits, the voltage is the same everywhere. So since we know it's a 12-volt battery, we also know the voltage drop across that resistor is still just 12 volts. That's the nice thing about parallel circuits, is that the voltage is the same everywhere, as opposed to series circuits where the current was the same everywhere. So now we could do Ohm's law again, where the voltage is 12 volts and the resistance through that resistor is 2 ohms. So there's actually 6 amps through this branch. There's 6 amps here. I would say there's 6 amps here. And if there's a total of 15 going into this junction, there needs to be 6 plus another 3, or half as much current, because it's twice as much resistance. So this would be 3 amps. Over here, 6 plus 6 is 12, plus 3 is 15. That's the total current. Let's see. Oh, we just did it. So what is the current through the 4 ohm resistor? If you're savvy enough, you could kind of look at it and see, but we could calculate it, do the same thing. So the 4 ohm resistor, R3, because it's the third one, is 4 ohms. The voltage is still 12 volts. Ohm's law, plug in. 12 divided by 4 is 3 amps, as we predicted. Okay, if it's twice as much resistance, it's going to be half the current. Okay. Number 8, the diagram below, 2 resistors. The ammeter is reading the total current, which is 20 amps, and it's 120 volt potential difference being supplied, and one of the resistors is 15 ohms. Now it's going to say, what is the equivalent resistance of the circuit? We could try to do this equation again, but if we're looking for the equivalent resistance and we don't know R1, that's 2 unknowns in one equation, so that's not going to help us. Again, we'll have to improvise, adapt, and overcome. Maybe this is a good opportunity to do a VERP table, because it'll help us see and look at the other information that they give us to see how we can figure out the equivalent resistance. You might already know we're probably going to do Ohm's law, R is equal to V over I. But since we're going to have to do other things, including the power, maybe we do the VERP table for this one to organize our thoughts. So again, I said this at the end of the last video. If you didn't watch the whole thing, that's okay. But we're going to organize the voltage, the current, the resistance, and the power into this nice table. And so those are the columns. There's going to be a row for each element in the circuit. So there's R1, there's R2, and then there's total. So this is like the first element, the second element, and then the total. This is a super helpful way. It looks like a lot more work. I write all this stuff and make a table. Like, why would I have to do that? If it's a little tricky for you, or if you get lost, or if you want to check your work, this is a great way. I highly recommend organizing your thoughts this way. And then it's kind of fun because it's like a puzzle. You're just plugging in the information. So the first thing that jumps out to me is I want to look at the resistors. So I don't know what the first resistor is, but I know that this is 15 ohms. And actually, part A is asking us for the total resistance, right? So we want to get that. Well, we don't have enough information right now in this column to get this answer. So we have to look elsewhere. What else do we know? We know the voltage, the total voltage is 120 volts. Oh, and that's super important information because this is a parallel circuit, and in parallel circuits, the voltage is the same everywhere. So actually, we could fill in the remaining columns over here, or rows, I should say, because you know the voltage everywhere is the same, and that's going to help us determine other things about resistor 2, resistor 1, all this other stuff. All right, they also tell you, and the table kind of cuts it off a little bit, but 20 amps is the total current, and I could tell us the total current. Not only does it say it in the problem, but it's not an ammeter here in this particular branch, or an ammeter here in this particular branch. The current's coming here, and then it gets split up here. It goes this way and then this way. So this is the total current at this ammeter is 20 amps. And it gets split up at this junction between the two resistors. So what can we figure out now? Well, the way you use this table is now once you've plugged in as much as you think you could plug in, you look at the rows. And anywhere there's two pieces of information in a row, you could actually calculate everything else for that row. So if our goal is to find the equivalent resistance, that's this box right here. Well, good news. I have two things in this row, so I know that I could calculate the other things, the equivalent resistance and the total power. So let's do that using Ohm's law. R is going to equal V over I. All right, so the equivalent resistance and the total current. So the voltage is 120 volts and the current is 20 amps. So this is going to be equal to 60 ohms. Oh, sorry, 6 ohms. 6 ohms, right? It's 120 divided by 26. All right, so now we could plug in. See how satisfying this is? We can like plug in numbers now, and we're kind of filling in the rest of the grid. And it says, what is the resistance of R1? Well, in this row, I don't have enough information. Ooh, so maybe what I said before was wrong. Yeah, I don't have two pieces of information in that particular row, but look at this. We have everything we need in this column. So we're going to go back to our equivalent resistance formula and calculate it that way. But you got to make sure you plug in the information in the right spots. 6 ohms is the equivalent resistance, so we actually plug that in right there. And we're looking for R1, and we have R2 is 15 ohms. Well, again, you're still just doing algebra. You're solving for R1, so to isolate this variable, what we're going to do is subtract 1 over 15 from both sides. They're just numbers. Even though they're fractions, don't be intimidated by them. So in your calculator, you could do 1 over 6 minus 1 over 15, and you could pop out a decimal, or you could find a common denominator and do the subtraction. Maybe you want to make the common denominator 30. Totally up to you. So when you do that, you get 1 over R1 is equal to, the calculator pops out 0.1. But again, we're not done. We have to find the inverse of this. So you do R1 is equal to 1 over 0.1, which is going to be 10 ohms. So that we could plug in 10 ohms right here. And we're almost there. We're ready to solve the rest of this table, but C just says, what is the power dissipated by the 15 ohm resistor? Well, we have, for the 15 ohm resistor, we called that R2, so we're looking at this row, and we want to know what the power is. So sure, we could calculate the current if we wanted, but we have enough information. We have the voltage, the resistance, we're looking for power. So we have to find an equation for power for the voltage and the resistance. So we're looking at our power equation here. We have voltage and resistance. We don't have the current, so we can't use this version or this version. We're going to do P is equal to V squared over R. And we could substitute in, and you get 960 watt is the unit of power. That's right, it's watts. Watts, okay. All right. Moving right along, number 9. An 18 ohm resistor and a 36 ohm resistor are connected in parallel with the 24 volt battery. A single ammeter is placed in the circuit to read its total current. And they're asking for the equivalent resistance and the total power. Whenever they don't give you a diagram, I highly recommend drawing your own diagram. So it should look something like this, where the 18 ohm and the 36 ohm resistors are connected in parallel, not in series, with the 24-volt battery. But the question is, where is this ammeter going to be placed to read its total current? So you could place it anywhere on this part right here. You don't want to place the ammeter on this branch or over here. Those would both be incorrect, because this branch reads the current in the 18 ohm resistor, and that red branch will read the current through the 36 ohm resistor. So you want it where the black wires are. So we could put it right here. You just draw an A with a circle around it. That's measuring the current. It's an ammeter. So it says, what is the equivalent resistance of the circuit? So we have enough information to just do the 1 over Req formula. And if we're feeling sassy, we could do the common denominator way. So 18 times 2, that's going to give us 36. That's a common denominator. And we could actually do 2 over 36 plus 1 over 36. So common denominator, add the numerator, and then keep the denominator the same. We have 3/36. That's equal to 1 over Req. So to get Req by itself, you just flip it around. So you get 36 divided by 3, which is equal to 12 ohms. Kind of satisfying that the fractions will work out like that. And most of the time when the people are writing these problems, if they're nice, they'll give you some nice numbers that you could do that fraction flip fanciness with it. But again, you could just plug in the numbers in your calculator if you want. It would look like this. You get 1 over Req is equal to 0.083 repeating, very messy, very weird number. And then you got to take the inverse, or you could cross multiply and solve if you want. But Req is going to be equal to 1 over that weird number with the repeating decimal, and you'll still get 12 ohms. So either way you want to do it, you could either do the fractions or just plug it in your calculator and deal with the decimal. That's fine too. Now they're asking for the total power dissipated by the circuit. So if they're asking, anytime they're saying like total, you definitely want to make sure you're doing the equivalent resistance. So I'm just going to like kind of do the guess method on the side here. We're not going to use this one or this one. We're using the equivalent resistance again because they're looking for the total power. And we could use the voltage. It's the same everywhere because it's a parallel circuit. So that's totally cool. And again, we have enough information now. It doesn't matter. This was like actually excess information about the ammeter. Who cares? We could still do P is equal to V squared over R. You plug in, and you get 48 watts. Nicey nice. Okay, done with the parallel. Should we do part 3? Part 3 is very closely related to parallel circuits. So yeah, parallel circuits continued. Kirchhoff's current law. If you see a problem like this, you should be very happy, I think, because as long as you know how to handle these, shouldn't be too tricky. It's all about the direction the arrows are pointing. This is super important to know. And actually, it's kind of frustrating because the first one we throw at you, it's very hard to see what direction these little tiny stupid arrows are pointing. But it's very important to know. It matters a lot. So if you can't make out what direction the arrows are pointing, that's probably leading to some confusion. Sorry about that. We have to get some better diagrams on this. But it says, okay, so it's giving you a definition. The total current entering a juncture has to equal the total current leaving the juncture. That's cool. Number 10, which diagram below shows correct current direction in a circuit segment? Hint, look at the arrow direction. How could we look at it if it's not? Let me draw it this way. So here, this is supposed to be going in. This is coming out of the junction. This is coming out of the junction. So we have in and out, let's say, for this. Okay, there's 2 amps in, and there's 5 plus 3, there's 8 amps out. That's no good. It has to be equal to each other. The same amount of current going into the junction has to be equal to the same current coming out of the junction. So here, let me zoom in kind of. This is pointing this way. This is pointing this way. And this is pointing this way. So in, how much is coming in? The 2 amps is going into this junction, and the 3 amps is going, it's pointing towards point P. So we have 5 amps total, and out we also have 5 amps. So B is looking good for a correct current direction. Okay, how about here? We have 2 amps going in plus 3 amps going in plus 5 amps going in. There's 8 amps coming into this thing and no amps coming out. That cannot be. Where are all these electrons going? They're all just going to build up at point P and there's going to be like 1 billion electrons there. That's not how circuits work, folks. Okay, so we got 2 amps coming in here, 3 amps coming out, 5 amps coming in. This kind of looks promising, I guess. What's 2 plus 5? 2 plus 5 is 7 amps coming in, and then out, that's 3 amps. Nope, can't be that. Can't be that. Has to be part B. That's how you do these. It's all about the direction of the arrows. How much current's going in and how much current's going out. So you could do number 11, similar concept, but it's a different way to ask the question. It says, what is the reading of ammeter A in each diagram? Well, let's do the in-out thing, and I'm just going to copy that over for the rest of them. So let's see what we got for this first one. We have 3 amps. I'll do 3 plus 6 coming in, 4 amps coming out. So what is that? 9 in, 4 out. So to make this equal, this has to be 5 amps. You need another plus 5 coming in. Okay, or sorry, going out. So this would be this way, 5 amps. Okay. For this second one, we have, how many are coming in? 6 amps plus 2 amps coming into that point. All right, at this point here, we're looking to see these 2 arrows are pointing towards that junction. And then 5 amps is pointing away from that. So there's 5 amps away. So what's 6 plus 2? That's 8 total coming in. There's only 5 going out. So we have to add 3 amps. That's what current in ammeter A is reading. 3 amps going out. It's like a balancing act, okay? Oh man, so many arrows on this one. Let's see, what's going in? 2 plus 3. 4 is coming out. 1 is coming out. 2 is coming out. Okay, so that's no good. I'll do, look at me with the fancy color move here. All right, 4 amps coming out. 1 amp coming out. 2 amps coming out. So we have 2 plus 3 is 5, where I come from. 4 plus 1, that's 5, plus another 2. That's going to be 7. All right, so we need another plus 2 to make it equal. Another 2 amps coming out. 2 amps. 2 amps going in. Okay, to make it equal. The answer is 2 amps. Hopefully you kind of get the idea how to do those now. Once you get the trick, it shouldn't be too tricky. Should we do part 4? Let's do part 4. And then in the next video, I'll do, equivalent resistance, kind of beefy. And then I'll do part 5 and 6 in the next video. Okay, finishing up with part 4, ammeters and voltmeters. It says, in order to measure current, ammeters need to be connected in series. Why do you think it's important to connect ammeters in series rather than being connected in parallel? Hint, think about how current in a series and parallel circuits differ. Well, if you look at the relationships in your reference table, in a series circuit, the current is the same everywhere. And they're saying, why would you want the ammeter, which measures current, to be in series, connected in series with your circuit? Because you want the current going through your ammeter to be equal to the current in the circuit that you're measuring. So for example, let me make a little circuit here. If I wanted to measure the current in the circuit, I would put the ammeter right here. Because I know that since it's in series, it's like in line with this resistor and the battery, it's going to have the same current as the resistor and the battery. I'm not going to change the current. In parallel, if it was in parallel, like a voltmeter is measured in parallel, we would say, okay, from this point, and then I put my voltmeter here, I'm like adding some wires here to this point. It's a voltmeter is measuring voltage. So the voltage across this resistor is equal to the voltage through this element that we just added, the voltmeter. Okay, so the ammeter is always measured, let me make it nice, in series, so the ammeter here, and the voltmeter is always measured in parallel. It should look like that. So we could say ammeters are connected in series so that the current running through them is equal to the current that they're trying to measure. You wouldn't put them in parallel because that things in parallel have different current through each branch. So you don't want to have a different current, you want the same current. Similarly, it says in order to measure voltage, voltmeters need to be connected in parallel. Why do you think it's important to connect voltmeters in parallel rather than being connected in series? So we could say voltmeters are connected in parallel so that the potential difference across them is equal to the potential difference they are trying to measure. So that's kind of the concepts with the voltmeters and ammeters and how you would connect them to measure what you're trying to measure. So how would that look like in multiple choice questions? Kind of like this. It says which circuit could be used to determine the total current and potential difference of a parallel circuit. This is looking good to me. Ammeters in series. The voltmeter is in parallel, but we want to know the total current and the potential difference of a parallel circuit. This voltmeter is only measuring the potential difference across this resistor, not both of them. I would like it to be more like that. All right, so to me, this is close but no cigar. All right, the voltmeter here is measured, is put in series, so that's definitely not right. Same here, that's no good. Okay, what about this one? Oh, what's the difference here? For D, the resistors are placed in parallel with each other. In part A, the resistors are placed in series with each other. So we kind of have to be super comfortable with and well practiced with the relationships in series and parallel to realize that the voltage across this resistor is the same as the voltage across this resistor, which is the same as this voltage because they're measured in parallel. So even though this voltmeter is still just measuring technically over one resistor, we know that it's going to be the same voltage as this, and it's the same voltage as the total voltage because they're put in parallel with each other. Whereas in series, okay, the total voltage is split between these two. So if this was like 2 volts and 2 volts, this would be a total of 4 volts. But if this is 4 volts, this is 4 volts, and this is reading 4 volts. So it's still measuring the total voltage, which is what we were looking for. That's why D is the better and the correct answer. 15, kind of a similar question. It says, which circuit diagram shows voltmeter V and ammeter A correctly positioned to measure the total potential difference of the circuit and the current through each resistor? So now we're looking for the current through each resistor and the total potential difference. So for A, this is looking good. It's measuring the voltage across both resistors, which technically that's going to measure the total voltage drop. So that's cool. Oh, and then this ammeter is measuring the current in a series circuit. So the current's the same everywhere in a series circuit. So they didn't say like measure the total current because it's the same everywhere. All right, so that's kind of a tricky one. A is looking pretty good to me right now. Let's see why B is not good. Oh, ammeter A is not connected in series. It's connected in parallel. And voltmeter V is connected in series. Not like it's just not good. That's not how you connect either one of those. Same with this. This is connected in series, and this is actually looks like it's connected in parallel. So again, that's not good. That's the opposite of how you would want to connect them. In D, ammeter A is measuring the total current of the whole circuit. If you wanted to measure the current through each individual resistor, you'd have to put an ammeter in both positions there. Not only that, voltmeter is not connected in parallel, so that's no good. Can't be the D either. A is correct, measuring the total voltage, and it's still the current through each resistor because the total current in a series circuit is the same everywhere, so it is telling you the current through each resistor. 16. In which pair of circuits shown in the diagram below could the reading of voltmeters V1, V2, and ammeter A be correct? So now you have to do a little bit of math. So there's different ways you could look at this. You want to take a look at all the series circuits and see if you could figure out which is not looking right to you. The first thing I would do is look at the voltages. So here I see a series circuit, okay? 50 plus 50, that's 100. So that's looking good to me so far. Let's see if the other ones. Here, the total voltage is 100. Well, these are connected in parallel, so this should be 100 and this should be 100. So, you know what? Choice C is not going to be our answer. This is no good. How about B? Okay, let's see. Does 50 plus 50 equal 50? No, in a series circuit, the voltages should add up to a total voltage, so it can't be B. And then in D, they're connected in parallel, so 50 volts, 50 volts, 50 volts, the same. The voltage is the same everywhere. So B, A, and D right now are looking pretty good. And that's the answer we're going to go with. Choice D, circuits A and D. Okay, cool. Number 17. Which circuit below would have the lowest voltmeter reading? So let's look at the differences in these circuits. These two are series. These two are parallel. They all have 6 volts supplied. So if we're looking for the lowest voltmeter reading, okay, we know that in series circuits, the resistors have to kind of split up this total voltage. So each resistor is going to have less than 6 volts. Because it's like what, maybe it's 3 volts plus 3 volts is equal to 6 volts. That's how it works. All right. In parallel circuits, okay, the voltage is the same everywhere. So this would actually read 6 volts. We know that. This would read 6 volts. So if we're looking for the lowest voltmeter reading, we can eliminate C and D because we know with A and B, it's only a part of the 6 volts. So where would it be the lowest for between A and B? Well, the current is the same everywhere in a series circuit. So they're saying like which one would the 20 ohm or the 40 ohm resistor need more, which one needs more voltage to push the current through at the same rate? All right, which is required. And listen, you could calculate stuff at this point, but let's just look at it conceptually, okay? All right, so which one of these resistors is going to use up more of the power to get the current going through? Which one's going to use more? All right, this is going to use more voltage to push the current through at the same rate as this one. This one uses less voltage. So it's going to be choice A. And if you want, you could calculate it. The way I would do that is to find the equivalent resistance. It's just 20 plus 40. And then you can find the current, I is equal to V over R. So you get 0.1 amps. And then for each resistor, you could find the potential drop across each resistor by using the same current, because it's a series circuit, the same current everywhere, but then you use a different resistance. So for resistor 1, the potential drop is 0.1 amps times the 20 ohms, and that gives you 2 volts. And for resistor 2, it's going to be 0.1 amps times 40 ohms, so that's 4 volts. And we know we did it right because 2 volts plus 4 volts gives you the total voltage 6. But as you can see, it's going to be the lowest voltmeter reading is for the 20 ohm resistor. That's why it's choice A. All right, in the next video, I'll do the part 5 and part 6 with the equivalent resistance. And I think that we're drawing some circuits in the other one. So this video is long enough. Have a great day.